Hello, and welcome to Go Beyond A&P. Over the next several minutes, we're going to build a clear picture of how the human body defends itself against infection. Not the immediate frontline barriers, that is for another video, but the specialized learned defenses we call adaptive immunity. In other words, adaptive immunity is a part of the immune system that learns to recognize specific invaders like bacteria, viruses, parasites, toxins, allergens, and more, and then it responds more effectively if it sees those same specific invaders again. So I want you to think of adaptive immunity as a strategic defense dashboard. Unlike the innate immune system, which reacts the same way to almost any invader, the adaptive immune system is very precise. It identifies a specific threat, builds a tailored response against it, and critically and systematically, it remembers that threat for the future. The antibodies you see on the screen are the signature molecules of the system, Y-shaped proteins, each one shaped to lock onto one particular pathogen. Here's the roadmap for this video. We'll organize every form of adaptive immunity into one framework. We'll see how the body builds its own defenses through infection and vaccination, and how protection can also be borrowed, such as passed on from a mother to a child or given by a clinician. By the end, you'll be able to place real-world examples, a childhood illness, a flu shot, a newborn's protection, or a rabies exposure into the right category and explain why each one behaves the way it does. So before we go into detail, let's establish the master framework, this matrix of immune acquisition. Every type of adaptive immunity can be sorted along just two questions, and that gives us a simple 2x2 grid. The first question, as you see in the rows, is, did the body do the work itself, or did it receive already made protection? Active immunity means your own immune system does the work. It recognizes a threat, it builds a response, and it usually creates memory for that threat. Passive immunity means the antibodies are already made somewhere else and transferred to you. In short, active means you build the weapons, passive means you borrowed them. The second question, depicted in the columns, is about the source. Was the immunity acquired naturally, like through ordinary life events, like catching an infection or being born, or artificially, like through a deliberate medical intervention? Now combine the rows and columns and you get 4 quadrants. Naturally acquired active immunity means you catch disease and recover. Artificially acquired active immunity means that you've been vaccinated. Naturally acquired passive immunity means antibodies crossed over from mother to baby. And artificially acquired passive immunity means a clinician injects or ready-made antibodies into your body. So keep this grid in mind because the rest of the presentation simply walks you through these 4 boxes one at a time. But remember the key phrase. Active immunity is about building weapons. Passive immunity is about borrowing those weapons. So we're going to start in the top left quadrant, naturally acquired active immunity. This is the oldest and most fundamental form, the immunity that you gain by contracting a disease and naturally living through it. So follow the cycle on the screen. It begins with pathogen exposure. You encounter a live, disease-causing organism in the environment. That can lead to clinical illness, the pathogen replicates, and while your immune system is still building its response, unfortunately, you get sick. This is the costly part of natural immunity. You pay for the protection by going through the disease process. Next comes pathogen clearance. As your adaptive response finally identifies the specific invader, produces specific antibodies, and eliminates it, that's recovery. An antigen is any recognizable piece of a pathogen, often a protein or other surface molecule that immune cells can detect. An antibody is a Y-shaped protein that binds to that antigen. But the most important step is the last one, lifelong cellular memory. Your body doesn't win the battle and forget it. It files away a permanent record of that pathogen. So the defining trade-off here is this. Natural active immunity is generally durable, often lifelong, but you have to survive the full-blown illness in order to earn it. That single limitation, the requirement that you have to get sick first, is precisely the problem that vaccinations were invented to solve. And we'll come to that shortly. So let's zoom in on that memory step, because it's a cellular heart of adaptive immunity, this architecture of permanent memory. When a pathogen antigen is first encountered, a naive B cell that happens to recognize it becomes activated. B cells are a type of white blood cell, a type of lymphocyte, specialized for antibody-based defense. That activated B cell then divides and differentiates down two very different pathways. The first path produces these things called plasma cells, the active antibody producing version of B cells, or short-lived antibody factories that pump out large amounts of antibodies to fight the current infection. The second path produces memory B cells, long-lived backup copies that can persist for years, even decades, quietly waiting for that same antigen to appear again. Now look at the graph, because it kind of tells the whole story. On first exposure, you get the primary response. It's slow, there's a lag of days to a couple of weeks, while the naive cell wakes up. And the antibody level it reaches is relatively modest. That delay is why you get sick the first time. But on second exposure, the memory cell drives the secondary response. And the difference is dramatic. It is much faster and it climbs to a much higher antibody level. The pathogen is neutralized so quickly that in some cases, or in most cases, you never develop symptoms at all. That gap between the primary and secondary curves, faster and stronger the second time, is the key idea behind adaptive immune memory. Every vaccine we discuss is designed to create that memory without making you go through that dangerous, sometimes dangerous, primary infection. And that brings us to the second quadrant, artificially acquired active immunity, better known as vaccinations. And this is where immunology gets clever. So recall the fundamental problem from natural immunity. To get durable protection, you have to survive the actual disease. Vaccination is an elegant solution. A vaccine is a biological product that safely induces an immune response, conferring protection on subsequent exposure without causing the disease itself. Look at the contrast on the screen. On the left is the threat or the live pathogen, which can cause real clinical illness. On the right is the blueprint, the vaccine antigen. The vaccine presents your immune system with recognizable pieces of the pathogen or with a weakened or inactivated form of it, so the system learns what to respond to without facing the fully dangerous version of that pathogen. And here's the crucial point at the bottom. The output is identical. Whether your immune system learns from the real infection or from the vaccine, the end result is the same. Permanent memory B cells, the same durable protection, but with a vaccine, you get there without the clinical illness, the complications from the primary disease, or even the risk of death. You get the memory, but you get to skip the disease process. So how does an injection in your arm turn into lifelong protection? So let's trace the vaccine activation pathway step by step. It starts at the injection site. The vaccine antigen is deposited into muscle, and the local immune cells, especially antigen-presenting cells like dendritic cells, recognize it as foreign and capture it. Antigen-presenting cells are immune cells that pick up foreign material and show pieces of it to lymphocytes, almost like presenting evidence of bad material or bad cells. Those cells then move to the second stage, trafficking to the lymph nodes. This is where the real immune education happens. Inside the lymph nodes, the antigen-presenting cells display fragments of the antigen to T cells and B cells, activating the specific cells that can recognize this pathogen. The B cells then proliferate, mature, and refine their antibodies. Finally, we reach storage. The freshly generated long-lived plasma cells migrate to the bone marrow, where they can continue secreting protective antibody for years, while memory B and T cells circulate throughout the body. So the pathway is detect at the injection site, educate in the lymph nodes, and store in the bone marrow. That sequence is why protection from a vaccine appears over a couple of weeks, not instantly, and then endures. All right, so now let's step back from the individual cell and look at what vaccination has done at the scale of the entire population, like this epidemiological impact. So each graph shows cases of a disease over time, with the red line marking when routine vaccination was introduced. Look at diphtheria, polio, and measles. The pattern is the same each time. Case numbers were high, often devastating, and then after vaccination began, they dropped sharply towards zero. These are not projections, this is history. This is the historical record. The World Health Organization estimates that current immunization programs save on the order of around 2 to 3 million lives per year. But there's a second, more subtle effect captured at the bottom of the slide. It's called herd protection. When you vaccinate enough individuals in a population, the pathogen can no longer find a chain of susceptible hosts to move between. Transmission is interrupted. That means even people who can't be vaccinated, such as newborns or people with weakened immune systems, they're going to be shielded because the disease simply can't circulate. This is the endpoint of active immunity. By artificially inducing memory across a whole community, we've driven some of the history's deadliest diseases to the brink of eradication. So we've now covered both forms of active immunity, natural infection and vaccination. At this point, we've crossed a fundamental dividing line in our matrix, moving from the top half to the bottom half, from active immunity to passive immunity. So I'm going to call this shift from independence to dependence. Here's the essential difference. In active immunity, the body performs the metabolic work. It sees the antigen, activates its cells, and generates its own antibody response. Because it does that work, it creates the memory B cells, and the protection is permanent. In passive immunity, however, the body bypasses that entire process. It does not build anything. It receives finished antibodies made somewhere else and uses them right away. And this is the critical difference to hold on to, because no antigen activated the body's own immune machinery, no endogenous immune response is triggered. Endogenous just simply means produced from within the person's own body. So since that self-generated response does not occur, no memory B cells are created. That single fact dictates everything about how passive immunity behaves. The protection is immediate. You don't have to wait 2 weeks for a response to build because the antibodies are already there and working. But it's also temporary. Borrowed antibodies are gradually broken down and cleared, and with no memory cells to replace them, protection simply fades. Immunity or immediate but short-lived. And that's the signature of every passive mechanism we're about to examine. So let's begin with the natural form of borrowed immunity, naturally acquired passive immunity. This is the most important biological example of antibody sharing, and it is one of the reasons newborns are not defenseless. It's the natural temporary transfer of a mother's antibodies to her fetus and infant, bridging the window before the baby's own immune system fully matures. Immunoglobulin is just another word for antibodies, and the letters like IgG or IgA refer to different antibody classes with different jobs. It happens in two distinct phases, shown on the left and right of the slide. Phase 1 is prenatal, or before birth. Here, the mother's immunoglobulin G, or IgG, is actively transported across the placenta into the fetal circulation. IgG is the main antibody class found in the blood, and it is the major antibody class that crosses the placenta efficiently. This is why a full-term newborn arrives already carrying a broad sample of its mother's antibody repertoire. Phase 2 is postnatal, or after birth. Once the baby is nursing, a different antibody, secretory immunoglobulin A, or secretory IgA, is transferred through the mother's colostrum and breast milk. IgA is especially important at the mucosal surfaces, like the moist body linings, like the gut and the respiratory tract, where many pathogens first try to enter. Rather than circulating mainly in the blood, this antibody coats the surfaces and helps block infection locally. So nature covers the newborn on two fronts: IgG in the bloodstream from the placenta, and secretory IgA on the mucosal surfaces from milk. So over the next two slides, we'll open up each of these mechanisms and see exactly how the molecules move. All right, let's take a look at the prenatal pathway apart at the molecular level, because it's a beautiful piece of cellular engineering. The star of the show is a receptor called FcRn, the neonatal Fc receptor. And the process is transcytosis, ferrying IgG across the placental barrier. Follow the four numbered steps. So step 1, internalization. Maternal IgG from the mother's blood is taken up into little pockets called endosomes. Inside the I can never say this word, syncytiotrophoblaст. It's the cell layer that forms the placental interface. Transcytosis simply just means transport across the cell. It's like endocytosis and exocytosis all within one cell. So transcytosis simply means transport across a cell. So in this case, IgG is being carried from the maternal side of the placenta to the fetal side. Step 2, acidic binding. As that endosome matures, its interior becomes acidic, dropping to around a pH of 6. And here's the elegant trick. IgG only binds tightly to the FcRn receptor at that low pH. So the acidic environment is what makes the antibody grab onto its shuttle. And that binding also protects the IgG from being degraded inside that cell. Step 3 is membrane fusion. The endosome travels across the cell and fuses with the membrane on the fetal side. Step 4 is release. The fetal side environment is at the higher, more normal physiologic pH of about 7.4, and that pH is the And at that pH, the IgG lets go of the FcRn and is released into fetal circulation. The pH difference between the two sides is the entire engine of directional transport. And notice the takeaway at the bottom. IgG is the only antibody isotype that can efficiently cross the human placenta. That is why maternal vaccination strategies against pertussis and tetanus, for example, are timed to the third trimester, when IgG transfer to the fetus is especially important. The goal is to maximize the amount of protective IgG ferried across to protect the baby during the first vulnerable months of life. Now, the second postnatal mechanism, the shield delivered through milk, built on secretory immunoglobulin A or secretory IgA. So trace the sequence on this slide. First, postnatal transfer. After birth, secretory IgA dominates the protective antibody in the mother's colostrum. That first antibody-rich milk and continues in mature breast milk. So notice the structure. Unlike IgG in the blood, this IgA is dimetric, two antibody units joined together, which make it especially suited to guarding wet mucosal surfaces. Second, receptor binding and transport. To get milk in the first place, the dimetric IgA attaches to a receptor, the polymeric immunoglobulin receptor, on the mammary gland's epithelial cells and is carried through them. During that journey, it picks up a protective piece called the secretory component, which shields the antibody from being broken down by the digestive enzymes. And that's what brings us to the clinical significance at the bottom. This is the key point. When the infant swallows the milk, the secretory IgA is not absorbed into the blood. Instead, it stays right there, coating the lining of the baby's gastrointestinal and respiratory tracts. It acts as a local mucosal barrier, neutralizing pathogens at the exact surfaces where they would otherwise invade. So breast milk provides a continuously renewed frontline shield for as long as the infant nurses, a perfect complement to the systemic IgG delivered before birth. We now arrive at the final quadrant of our matrix, artificially acquired passive immunity. This is the medical mirror image of maternal transfer. Instead of a mother providing antibodies through biology, a clinician provides them through a needle. As the slide describes, this immunity is obtained via the direct medical injection of exogenous antibodies, human or animal immunoglobulins, that were harvested from an immune donor and concentrated into a product. Exogenous just simply means they come from outside the patient's own body. So why would we do this instead of vaccinating? The answer is timing. This is used after exposure when someone has already encountered a high-risk pathogen and there's simply not enough time to wait the couple of weeks an active response would take. The ready-made antibodies provide immediate neutralization, bypassing the usual delay and getting protection into the patient before the disease can take hold. But we pay the same price as all passive immunity, and the slide states that the crucial clinical distinction plainly. No immune response is evoked in the recipient. The body doesn't recognize the pathogen and forms no memory B cells. So this protection is a temporary bridge. It's powerful and instant, but destined to fade as the borrowed antibodies are cleared. It buys the critical time, but it does not confer lasting immunity. So let's make this concrete with real clinical tools. The interventions we reach for when there's an immediate threat and no time to build an active response. Three classic examples are on the screen. First, gamma globulin. Pooled human immunoglobulin containing the combined antibodies of many donors used for broad exposure protection or for patients who cannot make enough of their own antibodies. Second, RIG, rabies immune globulin, infiltrated directly into a wound and around a bite to neutralize the rabies virus locally before it can travel into the nervous system where it would become untreatable. And third, HBIG, hepatitis B immune globulin, given, for example, to a newborn of an infected mother to help prevent transmission at birth. Now, look at the graph because it captures the defining limitation. When you inject these antibodies, protection is immediate. The level jumps straight up to a high protective titer, but from that moment on, it only declines. There is no immune response underneath to replenish it, so the curve steadily moves downward as the antibodies are metabolized and protection lasts only weeks to a few months. So what is the clinical takeaway? These products are an emergency shield, a high titer, an instant defense against an immediate threat. Where the situation allows, they're often paired with a vaccine so that the borrowed antibodies protect the patient right now while the patient's own active immunity is given time to build for the future. Let's bring everything together with the synthesis matrix. Every concept from this presentation lives in this one table. Reading across the rows lets us compare all four types of adaptive immunity side by side. So let's start with the two active types. Naturally acquired active immunity from natural infection and artificially acquired active immunity from vaccination. In both cases, the antibody source is self. Your own body makes them. Both produce a full immune response, and most importantly, both generate memory. That is why their time to protection is measured in days to weeks. You have to wait for the response to build, but their protection can be long-lasting, sometimes lifelong. The main difference is the cost. Natural infection requires going through the disease process, while vaccination aims to give you protective memory safely. Now to the two passive types, naturally acquired passive from the mother and artificially acquired passive from a clinical donor. Here the antibody source is from someone else, and this is the decisive column. Neither one evokes an immune response, and neither generates any memory. Because the antibodies are pre-made, the time to efficacy is immediate, but with no memory to sustain them, the duration is only temporary, weeks to months. So if you remember just one thing, remember this pattern. Active immunity is slower to start, but long-lasting because you build it and remember it. Passive immunity is immediate, but temporary because you only borrow it. Every example, a childhood illness, a vaccine, a nursing infant, or an emergency antibody injection, fits into one of these four boxes. And once you know which box it belongs to, you can explain exactly why it behaves the way it does. So, thank you for joining me in this episode of Go Beyond A&P. Learn it for the exam, understand it for life. Until next time, stay curious and keep learning.